Welcome. So this question says these masses are free to move. So we have a 2 kilogram mass and an 8 kilogram mass connected by a piece of string. They pass over a massless, frictionless pulley, so they don't affect the problem. There is a 0.2 coefficient of kinetic friction between the block and the table. So there's some friction here, not a lot, but there is some. What is the tension in the string once the system is released? Okay, let's look at this a little bit more. I'm going to draw a slightly better version of this. So basically, I'll do it down here. So basically, we're going to have the block going around a pulley. And so this is going to be 8, which means that we're going to have a weight down here of 80 newtons. This is 2, which means we have a 20 Newton weight, and there's also going to be a Fn, which is going to be equal and opposite. And then we're going to have, there is friction, so it's going to be a frictional force, Ff. So we need to find the tension. It's the tension that pulls this block forward, and it's the tension that pulls that 8 kilogram mass back. It is equal and opposite forces. There's only one tension value. It just does what it needs to do inside the string. String is the most amazing thing, actually. It sends forces around corners effortlessly. And, you get a lot of respect for string when you've done a few of these problems. There's a bit of a layout issue with this, and that is the fact that that is a, well, what would you call that? A downwards pointing 80 newtons. Okay. This is an upwards pointing T. This is a right hand pointing T. Usually upwards is positive, right hand is positive. I thought these were equal and opposite, but they're both positive, and so on. The problem is we have a sign issue when we go around this corner. So the trick is you always stretch that curvature out. So we redraw our diagram. And we have 80 newtons there. We have 8 kilograms. We have my T and my T, which are now equal and opposite. We have our 2 kilogram there, which means 20, and which means normal, and then we have our frictional force. And I want to find this tension value. And first question, is this system in equilibrium? And the answer is it is not. It is accelerating. There's not balanced forces. It's free to move. I'm going to find, well, let's do that. Let's prove to ourselves that it's going to accelerate by finding this value of Ff. How can I find that? Down here in the corner, I say Ff is equal to mu k times Fn. So Ff is equal to 0.2 times Fn, and we can tell from, just simple observation that if it's a 20 Newton force downwards, there's going to be a 20 Newton force upwards, because we're not accelerating upwards or downwards from this table. The block does not suddenly speed into the air or suddenly plow itself into the table. So this is going to be 20. So Ff is equal to 4 newtons. So if we take this 4 newtons and put it up here, we can see we have 80 newtons pulling in one direction and 4 newtons pulling in another direction. So we're not in equilibrium. So what we say is, well, let's find T using the sum of the forces, well, on an object or a system of objects. So I got a choice. I can pick the 2, I can pick the 8. Doesn't matter. Let's pick the 8. The sum of the forces on the 8 is equal to the mass of the 8 times the acceleration of the 8. And that's a little bit of subscripting I made up. It's like you can make up your own subscripts. That tells me, oh, I'm dealing with the 8. And so now I've got to do the math, and I say, well, plus 80. That's one external force to the 8. What else is happening to this guy? Oh, we have another external force pointing in the negative direction, so we add that to minus T is equal to the mass of the 8, which is 8, times the acceleration of the 8. And I do have no idea what that is, so let's call that A8. Let's rearrange. T is equal to 80 minus 8 times the acceleration of the 8 kilogram mass. I don't know this acceleration, but let's find it. So I simply go to a second step. If I tried using the 2 kilogram mass, the acceleration of the 8 is not included, and there's also a T. I really want to, if I think about it, I have two unknowns. I have my T is unknown, and I have my acceleration, which is unknown. So I want to avoid the T. If I use this mass, T is included. If I use that mass, T is included. And so I come up with a really insightful idea, which is I say, let's just regard this as a system. Like, the front of your car and the back of your car connected by the chassis. That's the system. Now, Newton's law still applies, so I can say find the acceleration of the system using the sum of the forces on the system equals the mass of the system times the acceleration of the system. Now I wanted a 8, but this is not a piece of elastic, this is a piece of string. So the acceleration of the 8 is the same as the acceleration of the 2 is the same as the acceleration of the system. If it wasn't, these guys would get closer together or further apart because they had different velocities and they don't. So different speeds and they don't. So I can say, okay, so if I look at this, the plus 80 is that external force added to the minus 4 is that external force is equal to the mass of the system, which is 8 plus 2 times a system. So that means that a system is equal to 80 plus minus 4 is 76 over 8 plus 2 is 10, which equals 7.6 meters per second squared. And let's remind ourselves that that equals A8, and it also equals A2. They are all the same acceleration. So now I can simply say, oh, well, T is equal to 80 minus 8 times 7.6, which equals 80 minus, let me get my handy dandy calculator, 8 times 7.6 equals 60.8, which equals what is that? 19.2. 19.2 newtons. And if I look over here, yeah, the answer's there. It's D in this case. So there I have it.